good to be here. Welcome. My main interest in computer science all along, since I got into it when I was an undergraduate student, has been sort of in efficient ways of doing this or that. Neat problems, but neat techniques, neat algorithms. And now a lot of it's in sort of interesting representations that have major advantages over other sorts of things. So in our talks today, we're doing radically different sorts of things, and what I'm doing and starting the day with is sort of at a pretty basic level, sort of not the machine, but pretty close to it. And so it's a matter of representing information. If you've got something you want to represent, how do you put it into bits efficiently? So as you know, information is represented as a bunch of on-off devices. Bits. It's not three signals because, up, down, and even or something like that. And the only reason for that is that it's turned out to be easier to make two-state devices. There's nothing magic about two, although it dominates everything we do, except that it's a little easier. If you want to represent text, I'm going to focus on that rather than pictures because there's similar things to be said about pictures, but it's a lot more complicated, and I think I get the message across more talking primarily about thinking about individual characters. So text is usually represented by a standard encoding. You've got, on most computers today, you have things called bytes, and there are 8 bits in a row, and so that's 2 times 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 2. 256 possible things, and so in 8 bits, and so you could represent one of 256 characters. Things in that, and this fixed size. And for a long time that was done. In fact, for a long time they only used basically 128 of them in what's called an ASCII code, which is American Standard Mumble Mumble Mumble. American Standard 102 in Roman numerals is what it says there, but that's not what it stands for. And then, as people decided we want to be able to represent characters from lots of different alphabets, they developed a thing called Unicode a few years ago, and then they decided, we aren't going to restrict ourselves to the alphabets that people currently use in the world, because I think 16 bits would have done it. That's 256 times 256 characters. That's a lot. But they wanted to represent hieroglyphics and expand things, and now there are representations that take more bits for one character, because there are lots to do. But basically, these are fairly easy to work with. I mean, if you're thinking of just plain old boring Latin alphabet, you get away with fewer than 256 of them, so everyone's aligned on this nice little place, and the computer figures it out. You might as well think of them as letters. So they're easy to work with, and don't forget that virtue of simplicity. So we're going to represent data in a number, maybe the same data, in a number of different ways for different reasons. First is simplicity. That's fine. Another thing you might be concerned if you're transmitting information or if you're storing it on some device that conceivably could get lost, you might be concerned about some issues of privacy, or you might want to keep your information secure. That's another perfectly good thing you might want to do. And so when you're doing that, there are interesting mathematical things that have been done. Encoding was, one of the oldest ones known was called a Caesar code. So it's a couple thousand, certainly known by the Romans as a flipping letter for letter thing. Well known what went on in World War II as a lot of things on cryptography were developed. Now there's a standard method. There are twists on it and things. A technique developed by 3 people: Ron Rivest, Adi Shamir, and Len Edelman, all of whom I know quite well. So it's called RSA, and it takes information, character strings, let's say 1,000 characters. Takes that message and it says, I can think of this as being not a character string for now, but I'll think of it as a number. I can do arithmetic with it. Because if you've got bits, it's up to you to interpret what's going on. And if you think it's a character string and I think it's a number, the reality of the two meanings of the two things have nothing to do with each other, but it's still bits. And the RSA technique is based on doing some arithmetic on these bit strings, raising things to powers. It's crackable only if something we'd have no idea how to do efficiently can be done efficiently. And that is to factor if you've got a big number, that big, maybe even that big, that happens to be the product of two prime numbers, 2,000-digit primes. How do you factor them? Well, you don't try, is it divisible by 2? Is it divisible by 3? That would take substantially longer than the lifetime of the universe, even at a nanosecond rate of the fastest computer today. So there are no fast techniques. So that's an interesting idea. We are doing things, and security relies pretty heavily on the assumption that nobody has yet, or is likely in the near future, to come up with an efficient algorithm for a particular mathematical task. And a lot of security is based on that. The way around the security, truth is, anything to do with security, don't worry about the frontal approach, the attack. That's mathematically hard. The way it's likely to get cracked is coming in through the back door and doing something that's not supposed to be legal in the model, not supposed to be doable, but somehow there's a hole in the system. But for straight-up cryptography, this is a great technique. So that's one thing you might like about storing your information, that you have access to it, and if you happen to lose a device or it's picked up as it's being transmitted, it can't be interpreted. Another thing that you might like to do is that when you store things on a computer, there's some chance that there will be an error in a bit. And if you take a book and flip one bit in it somehow, or lose one bit in it somehow, you don't want to lose the entire bit. And certainly if you're transmitting stuff, bits are dropped all the time. Dropped meaning missing, flipped, extra one thrown in, and I mean, this is certainly a major issue for data transmission with Cisco and companies like that. So let's just have a little thought about this. You've seen some of this. If you've got a credit card, you'll know that if you just change a digit in the credit card, you don't get, usually, you shouldn't ever, if you change one digit or interchange two digits, get somebody else's credit card number. They're supposed to be check bits. Maybe I'm using a very simplistic thing. It's not what they do. But an idea would be if you had a 8-digit number, and we will just tack on another number, another digit, so that if you add all the digits together, you get something that's divisible by 10. The last digit is 0. Let's suppose you did that. That would be the idea of a check digit. And in fact, they do much more sophisticated things than that. That one, of course, I suggested, if you flip the order of two digits, which is really easy to do when you're giving a credit card number over the phone or something like that, or copying it down, you want to check those things. So there are things like error detecting codes that I would say a check digit does to some extent. There's an interesting and old technique called a Hamming code, another way that's actually kind of cool. I believe it was the first, that if you have a bunch of stuff to transmit, what we'll add is a very small number of extra bits on it. If you've got 10,000 bits to transmit, we'll add about 13 bits at the end. Not much of a change. And it has the magic feature that when you do some arithmetic on these things, you're actually solving some equations. is what's going on. You do some arithmetic on this. Now, if somehow one of those bits, any one of the 10,013, get changed, you can go back, but just one. You can go back, you can do some arithmetic, and the extra bits you've thrown in, well, it's not true. The extra information that you get out of this will tell you which one is wrong. It's kind of cool. 10,000 bits you want, 10,013, a little bit more. You change one of them. I've set them carefully, these extra bits, done some arithmetic, done some serious calculations to do that, and if there's an error, bang, I can pick it up. And that's what's done, that kind of thing is done routinely. There's not more recent, it's still old, technique called a Reed-Solomon code that you probably dealt with a fair bit. Compact discs use this kind of code for error correction. And they are kind of neat because I have not done this, and unfortunately I didn't get 100 or 2 CDs and nails and hammers, because the claim is if you take a CD and you fairly neatly and bang a nail through it, it's still supposed to be readable. I have not done this myself, but I have a friend in engineering, of course, who claims to have done this. And that's one aspect that you perhaps encountered. Another thing that I think is really cool about error correction is going to Jupiter. Anybody been there? No. Well, in the Voyager, whatever you call it, rockets or whatever the right word is, space probe going to Jupiter. In fact, going outside is it outside our solar system now? Not. Is it past the farthest planets? It has, okay. But when it was as far as Jupiter, which took 15, 20 years, it wasn't producing power at the rate that it originally had. It was producing power at about 260, 270 watts from Jupiter. And they wanted to send back pictures of what was being seen. This is 2 light bulbs or so, and you still got to run the rest of the spacecraft. So you have 2 light bulbs, and you're on Jupiter, and you want to send back a message. Pictures. Lots of pictures of what you've seen. Bits are going to get flipped. Things are going to get messed up. It's going through all sorts of things. Asteroid belt. Maybe, hopefully you've lined things up so that's not going to happen at the time. But you certainly got major problems with this transmission. And what they actually did, using these these codes, they had techniques that we've seen the pictures that are sent back from outer space, and they wind up sending about a couple of 100 times as many bits as what you can see. And so it turns out that close to half, and it's not just a simple majority, very sophisticated codes wind up being able to be decoded, and there are tons of errors in the information that's transmitted, but they go back and they find the right thing, which I think is kind of neat. So that's another thing you might like when you're transmitting data, and certainly when you send things over the internet, there are definitely error correcting codes going on. There are error correcting codes going on in this computer right now, as a matter of fact. Another thing you might like to have is being able to do operations easily. Some representations can be convenient to work with, others can't, others aren't. I'm just going to give one minor little example of something that's kind of cool. A thing called a gray code, and it's not that important, but it's an easy one to grasp. What I want to do is I want to represent numbers starting at 0, and I want to be able to add 1 or subtract 1. Well, add 1. And every time I add 1 to my number, I just want to flip 1 bit. I just want to change one thing. So if we had 0 to start out with, we might say, well, to get to 1, that's pretty easy. That only changed 1 bit. But if we did our standard things, to get to 2, we would change 2 of them. And to get from 15 to add 1 to 16, it would be like adding 1 to 9,999. To add 1 to 9,999 standard representation, you change 1, 2, 3, 4. Oh, you change 5 bits because the one out front has got to get changed as well. And if you were adding 1 to this representation of 15, which is 1 plus 2 plus 4 plus 8, that's what that means, then you would change them all. There are techniques, and there are a lot more interesting things to be done, but this thing, example I've got up here, we start out with 0, we add 1, and we get, we'll call it 1, and now we have to have we're going to have a different representation for convenience of a particular different operation, and we will represent 2 as the third thing down there, 1, 1. Because, and so if I say, oh, that represents 2, I don't care if you think it represents 3 by standard way of writing things. Then if I add 1 to 3, I'll write 1, 0. Sorry, 1 to 2. I'll get 1, 0. And then if I want to add 1 to that, I'll make it 1, 1, 0. And I'll just make up these. These are representations of numbers. The abstract concept of 27 is an abstract concept. We write it down that way. A lot of time you might think it was written down as, or somebody might, as that in binary. Not that some of you may be familiar with writing a number down in binary at 27 that way. Hopefully most of you are familiar with this notation, except for maybe a couple in the back. But here's a different one that has a different esoteric virtue. So that might be nice. And there are other things like representing numbers so you can do multiplication fast. There are techniques that would be of use there. That's nice. But what I'm really going to spend the next 15 minutes or so on is compact ways of transmitting data. So what I want to do is I want to store things and take less space. Now, you might say, gee, space is cheap. Well, that's true. Outer space, maybe. Or maybe even space on a disk in Australia or something, but space on your computer close to where the operations are, it takes a while to move it in. It takes quite a while to take things from disk, a few fraction of a second, but it's quite a while to take information off the disk in your computer and start doing actual operations with it. The faster memory that's that on your machine, the so-called cache memory, is expensive, and we don't have a huge amount of it. We're getting more, but every time we say we get some more space, we get bigger problems, or we expect things to be done faster. As I often say to my students here, is nothing's really changed about time and space in the last 40 years, except for the prefixes. We would say, oh, it's a few kilobits, or kilo words, or kilo somethings long. There's a few thousand. And now we might say, oh, it's a few petabytes, or peta whatevers long, and that's 10 to the 15th. And in a funny sense, I won't claim our problems have expanded by that degree, but the problems we're trying to solve, and we expect to solve instantaneously, have changed dramatically over the years. Our ability to handle them has changed dramatically over the years, but we still have a lot of the same basic problems. So I will say that smaller, one, gets it around the world faster, goes through fewer switches and all sorts of things like that, and it can often fit into smaller, faster memory. And so that's one aspect. I'm not going to give the long version of this, but data compression is an interesting little problem that has developed over the years, and as computers have developed and algorithmic thought, ways of doing things have been improved, the techniques, data compression has become much better, and the techniques used for it have become so much more sophisticated. All of the mathematical and approaches that have been, computing approaches that have been used have been developed over these years, and it seems like as you turn around, there's some new technique for doing something or other. It gets applied all over the place, and one of the places is data compression. There's one thing about data compression, one method I'll just mention briefly, and that is there's techniques where you take a book, sequence of characters, millions, whatever it is, and one way to compress it involves first reordering the characters. This sounds like you're really going to mess things up. You take a book and say, oh, well, let's put all the A's together. You don't put all the A's together, but pretty close to it. You reorder the characters, and that allows you to compress it. Well, yeah, there's 7 million A's, 14 million B's. I mean, yeah. But the idea is that it can be decompressed at the other end, which is kind of a cool, sophisticated technique. I'm going to talk about an older one, and that's called a Huffman code, named after a guy who, as I understand it, didn't want to serve in the American military. Sounds like a good idea to me. Not serving in the American military for various reasons, but we won't get into that here. But he was a student at the time and developed a data compression technique for sending signals, visual signals, from ship to ship. That was the original idea. There are a bunch of messages that they might have to send, and they wanted very succinct codes for them, and you wanted to know when you were finished with the code. So that's where these things came from, and then they became applied in various ways. And Huffman, he was alive a couple of years ago. Don't know if he's still alive. So, the idea. The idea is very simple. If you're going to give a message fairly often, why not have a short code for it? If it's not as often, you can have a longer code. And on average, you'll do quite well. So this our standard thing is if I want to send a letter, 8 bits or something like that, then if all letters are the same, then it guarantees I get a letter across in this amount of work. Not interested in that. I'm going to send a lot of stuff, so what I want to do is guarantee that for a big message, I will get that through quickly. Some of the individual characters may be really quick, but some may be slow. Hopefully, the quick ones are the common ones. And so the code lengths are going to vary. Now, there's an old code from the 19th century called a Morse code that kind of did that. It sent things in 2 types of signals. One was called a dot and one was called a dash. Well, what the heck? It could have been called a 0 and a 1. I don't care. But that's not quite the same thing. If you've seen old movies that may have this, we have up here the signal SOS, and the signal for an S was dot, 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 and the signal for an O was dash, dash, dash. Fine. Now look at the next line. Look at what I've got on the dots and dashes below here. Notice I had a little space after the S before the O started, and after the O before the next S started. We have little breaks there. Down below, all I've done is write the same sequence of dots and dashes, but I've put the breaks in different places. So I went dot, dot, which happens to be the code for an I. I don't know this stuff. I looked it up, okay? And then for an A, which is dot dash, an M, which is dash dash, an E, which is dot, and an I, which is dot dot. I just broke it up differently. And it means something completely different. You probably have friends who, when they talk, it's kind of like this. You know, you kind of don't know. They're talking so fast, and it's just totally confusing and perhaps more entertaining than what they were really trying to say, which, of course, is a virtue all on its own. But what we're going to do is slightly different. When you send stuff, write stuff in the computer, you're sending this stream of things, and there's a cheat in what I wrote here. And that is, there's really a third character I've got. I've got dot, I've got dash, and I've got blank. Oh, we don't have blanks in the game we're going to play. And so the whole thing is 3 dots, 3 dashes, 3 dots. In either case, you have to have a code for that. You don't get to put the spaces in. I guess in English, it's important here. If you take a sentence in English and you just remove the spaces, you will probably figure it out okay. You probably won't have any great problem. I mean, for that matter, if you take words in English and you drop the vowels, you probably understand them perfectly well. If you operate in Arabic or Hebrew, people do that for you anyway. So it works. But here, no, we've got 2 characters, dots, dashes, and there are no spaces, no extra stuff at all. And the other thing that Huffman wanted was to be able to sort of say, I've got a code for this, and when I read dot dash dot dot, or 0, 1, 1, 0, or whatever I said, translating it into either things, or A, BBA, or something like that, I want to know when I come to the end of a character. That's one of the rules I'll have, because actually what he was doing was dealing with transmissions from ship to ship, visual, and they wanted to know when they were done with a signal, with a message. And they were only sending one message. They had several thousand messages they might send and just wanted to have ways of doing this. So a bit more secure at the time. Okay, so there was this concept of things called a prefix-free code. And what that means is that no code can be just the beginning part of another. So there aren't any prefixes. No code is the prefix of another code. Which, of course, when you get prefix-free codes, people start giving shorter names for it, and they start calling it a prefix code, which is it's kind of a not prefix code, but what the heck, they called it that anyway. So it's the way terminology always goes. It gets a little, you understand what it means, but when you think about it, you often find out, well, that's not what it means. The words don't go through here literally. Okay, so we have that, and so the next thing we're going to assume, or you can do, you can say, well, what is the frequency of each character that you might be sending? If you had standard English text, there are, and you look at novels or something like that, the vocabulary used and all the rest of it, that, blanks occur 20% of the time, E's occur 12% of the time. I'm making all this up. But there are known and determinable probabilities, frequencies of things occurring. Or what you could do, if you had one document, just scan the whole thing quickly and count the number of times each thing occurs. And that would work perfectly well. So we'll assume we're going to do that. And now we're going to develop a code. So I'm going to give you a real specific, easy algorithm, but I hope you'll understand how this works, how we can develop these things. So, given that we are primarily in rows A through F, as you look up here, I will magically have my alphabet come from the letters of the rows, which is, of course, pure coincidence. And suppose, I just put arbitrary numbers down here, that A's occur, I've got those, yeah. A's occur 30% of the time, B's 25% of the time, D's 20% of the time, F's, C's, and E's. Obviously, this isn't standard words in English, but they're arbitrary frequencies. So what I'm going to do is wind up wanting to say A faster than E, because A's in my world occur 6 times as often. So I would like to be able to say it quite quickly. And what I would like to do, and I'm not going to have time to prove it, that's for sure, I want to get the best possible code which minimizes the average length of time to transmit a character, or let's say, in other terms, the amount of time it takes to send a few million characters. I'm going to get the fewest bits I can possibly get away with, and by developing a code. Not by having 8 bits to say, well, heck, I could get away with 3 bits for this alphabet. Not by saying A is 0, 0, 0, B is 0, 0, 1, C is 0, 1, 0, etc., or something like that. Not by having them all the same, but by having the frequent ones occur more often. So the algorithm for doing this is something I can explain in words pretty well. Or maybe I can explain it in pictures. So we'll start with that data, that information. And what we'll do is we will take the 2 least frequently occurring characters. I've initially put these in sorted order with the least frequent ones on top. Notice that wasn't alphabetical order, but was in order of increasing frequency. So the 2 least frequent ones are at the top. And I will simply say, all right, well, rather than having a code for an E and a code for a C, I will have a code for EC, either one of them, and I'll tack a 0 at the end for an E and a 1 at the end for a C. Is that reasonable? And the actual useful way of writing this is by a little picture, and the picture there with it shows that it's the EC that we have up there is going to be represented by something I don't know, and then they're going to diverge, and the E will go to the left, and lefts are going to be 0s, rights are going to be 1s. Simple terminology. There. Okay. And so that sounds reasonable. Now, EC occurs with the probability of it being either an E or a C, and it can't be both, so the probability is 0.05 plus 0.08, otherwise known as 0.13. So you just add those probabilities. And so I'll cross out the E and the C. I won't have to worry about them anymore. I'll know that the partial coding ends in a 0 or 1. Don't even worry about the partial coding. I'm just putting that on my slides. The picture is the part that really, the picture as I've got up there is saying what we want. Okay, so we have that. And now that was so much fun that we're going to do it again. We're going to take the 2 least frequently occurring things that have not yet been crossed out. And those are the F, as we see, and the EC. Boing. And so we will cross out the F, we will cross out the EC, and we will replace it by an FEC. And the idea will be that we'll have F, E, or C. The first few bits to represent either of them will be the same. But then after that part that is in common, to represent an F, you just put a 0. To represent an E or a C, you put respectively a 1 going to the right and a 0 to go to the left for an E, or a 1, 1 for a C. So it's actually pretty easy. And now let's look around and say, what are the two least frequently occurring things? Well, there's a probability of 0.2 for a D, and it's 0.25 for either B or FEC. There's a tie, doesn't matter. I'll get a different code, but they're equally good. And so just for purposes of illustration, I chose to take the D and the B. I wanted to do that, so now I've got a couple of other things merged together. So D and B are represented in the same way, except at the end of it, the last bit of a D is a 0, and the last bit of a B is a 1. And by the way, who goes left, who goes right, it doesn't matter. I just decided to try to keep it as simple as possible. I put the lower probability to the left and the higher probability to the right. It doesn't matter. Unless you lived in a world where it cost you more to transmit ones than zeros, which it doesn't for our purposes, but one could imagine it, like in the Morse code. Okay, so that was done. So the algorithm is, as is indicated there, it's a cook until done algorithm. You start up, you set up, you keep doing the same thing until you're finished. And so now I'll look for the least likely things, which are the A and the FEC. And no great surprise, what happens is I put them together. FEC had a lower chance, so I arbitrarily, but not necessarily, I arbitrarily put the FEC to the left and the A to the right, and we have that little tree diagram there to indicate them. So the deal is that A is going to be represented by some junk followed by a 1. Different junk than the B is, sorry, A will be, the B will be some junk, but different junk than A, followed by a 1. So I haven't finished these off yet, but I'm about to. So now I'm in the position of having precisely two trees, two objects. I take two of them out, I take the two lightest ones out, I gob them together, and I put it back in. So that means I've got one fewer object than I did before. Two out, one back in. And so now I look around, and I take the two least likely, which happen to be DB and FECA, and I put the ordering there so it reads from left to right, the names on the merged character thing. And I put them together, and the DB happens to have a lower probability, so I stuck it to the left arbitrarily, and I get this. And that is my, this diagram here indicates the code. So for the probability of getting one of DB, FECA is probability 1. And you notice that the letters happen to be ordered in such a way that there are no obscene comments on the example. That one must always check these things. Okay, so that would be fine. And now let me just do a small example, and you'll see an example later. So if I had the word face, then I wanted to represent that in this code. Now, by the way, that's got one of each of 4 characters, so this isn't going to be the greatest way to represent face, but if it was some long thing I wanted to represent with very few E's and lots of A's, then it probably would be good. So F I will represent. Now, all we do is take a look at that tree over there, and how do you get to the left, to an F? You go to the right. Right is a 1, left is a 0. Right, left, left. Everybody with me on that? Good. A, right, right. C, right, left, right, right. Right, left, right, right. See, I translated, I can use zeros and ones and lefts and rights and A's and B's and ups and downs. Doesn't matter, I just have to have two symbols I write. And now finally E, which, oh, I've got them written up there, but I'm looking at the tree. 1010. And there's my code. And ideally, for a long message with these probabilities, this would be pretty compact. It would take somewhat less space than the standard, and I would transmit it in that way and get down the line faster, cheaper, and all the rest of it. So that'd be a representation. Now, this is one thing. Now, you'll observe with this what I said, and this is the best you can do. But when I say anything is the best you can do, I have to define the rules of the game. And the rules of the game are that I have to have a code for each letter. When I'm done that letter, I'm done that letter. I don't mush together A's and B's, which can be done. And another thing, the probability of each character is a fixed value, and there are no correlations. Whoa, there's a problem there. In English, you see a Q, what's the probability that the next character is a U? Well, it just went up pretty high compared to what it would be if you hadn't seen a Q. You see a T, the chances of an H just shot right up. So we're assuming that that doesn't happen. And if that were the case, this would be the best you could do. It's not the case. So there are other much more sophisticated techniques that take advantage of these sorts of things. And we don't have time to deal with that, but this does give you an idea of a couple of things. One is it's a kind of a simple but neat algorithm, way of representing things. Another is that I'm telling you that under some certain constraints, it's the best you can do. And the third thing is, hey, are those constraints really the situation in my particular world? And that, in a lot of things in computing, we try to prove we've got the best possible technique. And you can prove it mathematically. It's one of the things I do. But when you do that, you better get the rules of the game right. And when you write down the rules so you can say, oh, this is the best under these rules, it sometimes tells you, hey, are those rules really correct? And if so, it might give me some hints of getting around those restrictions. And maybe I don't need those restrictions. That's going way up somewhere else. Okay, so we've had a look at that. And so I'd like to get you to play around with a few questions that you have in front of you. And I'll get you to do that for a few minutes, and then we'll go over the answers. The first question is just to take this Huffman code, and I'm going to go back to one of the slides that's developing the Huffman code and leave it up here after this question. So the first one is to take a look at this, an example. Fine. The second question looks long and hairy. The second question is the most colorful, at least, but this is a funny little quirk. What I have up there is a code, and it happens to read out as face feed, because I was trying to get something using only that was sort of English and used only the first 6 letters of the alphabet. Okay, and then what I did was I transmitted, and I dropped a bit. Oh my gosh. You flip a bit in a Huffman code, then or lose a bit, you're going to get all, your alignment between characters is going to get all screwed up. Right? They're not fixed length. They vary. And so you remove a 1 bit or you stick an extra 1 in, you flip a bit, the whole alignment can get messed up. But I just want you to walk through the same example of face feed and pretend and use those things and see what it decodes to. Okay, that's one thing. And the other thing, if you are done ahead of everybody else, a question I want to just toss out is, if you had one of these Hamming codes that I mentioned at the beginning, is a code, and you throw in a few extra bits, and those extra bits are just enough extra things to say, where's my mistake? This one is tougher, but that way people can work on the Huffman and they've got something to play with if they are ahead of everybody. Okay? So what I'll do is I'm going to back up to the middle of the development of the Huffman coding so you can refer to that. And if you got any questions, I'm here. Just ask. And oh, by the way, when you do this, do it in whoever you're sitting with. I mean, chat around, or two in twos, whatever number of you is convenient to talk to about this. Yeah, it's probably inconvenient for a person on this side to work with a person on that side, but that's data transmission. Okay, so let's take 10 minutes or so. So let's take a look. That way you can have a little break before the next question. Oh, determine a Huffman code for those ones. All right, I'll do this on this board. First, we have, okay, so remember, we take the two least likely things. And as somebody observed, gee, I don't use a C at all in there. And so if you were doing this from scratch, and that were a big, long abba-dabba, then you would say, well, C's don't occur at all, so I don't even have to have a code for them. That's absolutely true in that case, but that wasn't what I intended in this example. And so C's and D's are gee, in this example, it is true. They are the least likely characters to occur. And so we decided, well, what the heck? We will make it such that C's and D's have remember, the same code up to the end, and then they'll be different. And if we do that, that means it's probability 0.3. And now we have CD and A each occur with the same chances. Now, there are two. It does not matter whether you put the CDs to the left or the A's to the left. Unfortunately, I should have made a slight difference in the probability, so our convention would have caught us, and you would have all written the same thing down. But the answers are both absolutely correct, but the codes will be different. So let's just assume we did this one. You do the other one, you're also right, but we'll have to follow along. And finally, then there is a B, which occurs half the time. And again, I don't care whether the B goes left or right. Both are absolutely correct, but we'll give you different codes, and therefore when you try to encode abba-dabba, you'll get a different value. But also correct, and an advantage of having these, I will tell you, they will be the same length. The goal was to get a short code. There may be multiple choices that are equally short. They are equally virtuous. They are just different, and they're equally virtuous because they are the same length. No, neither is shorter or better than the other. And so if we do this, we get ba. And then we get D, which is 0, 0, 1. And I'm just underlining these so you get the idea. And now we have ABBA again. These 70s rock groups won't go away. And so that is A, B, B, A. And so that would be the encoding it. Now, the advantage of the fact that there's more than one correct answer to this, if you had a different one and flipped things around, you would see that for a B, that an A will be of length 2, no matter which way you oriented the zeros and ones. I think. A B is going to be of length 1. That's going to hold out. C's and D's are going to be of length 4, wherever they happen to go, although the flips of lefts and rights could make them different from what I've got here. But you would still have a correct answer. Well, you see, this is another thing that's sort of useful. You say, oh, I got the right answer. I found the shortest way to get from here to wherever it is, over in the math building. Well, there could be more than one way that are equally short. And so I'm not going to say one's right, one's wrong, by any means, or one's better than the other, and that's not the point at all. It just could be that there are different ways of different codes. Okay, any comments on that one? Now, here's an interesting one that most people don't ever think of. And it's just a curiosity that this deserves a remark. Now, we've got that all set up, and I've nicely got the picture sitting there so that the different colors go on. By the way, you don't transmit different colors of zeros and ones. They're just our picture there. So when we had, instead of 100, we messed up somehow in transmission. A bit was lost. It could have been flipped. Anything could happen, and this happens all the time. So you have error correcting codes. But I just wanted to do this in an example, the straight up thing, because something funny hopefully happens. I read 1, 0. Ew. It's going to be a little tricky to handle. 1, 0, 1. 1, 0 isn't anything up there. Sorry, 1, 0 is not the end of anything. 101 is not the end of anything. 101, 1 is a, sorry, that's 10. Yeah, 1011 nicely works out to be an A. Now, something curious happened here when I lost that 1 bit. Rather than having 10 for a, sorry, 100, which would be an F, and a 11, which would have been an A. Just coded that. I had a 1011 instead of, rather than an F followed by an A, I got a valid thing for a C. Could happen. You could get the wrong information, and it's perfectly valid. And furthermore, we happen to notice here, because of the magic of colored stuff, we are all aligned again, and we'll read the baby blue 1011 and decide that that's another C. And so that the next character would be C. So it would have been, what we would have translated that is C, C, E, feed. So what would have happened in this case, if this mistake were made, it would just happen to have completely realigned. It would have written a wrong character. It would have been one, in this case, one wrong character rather than 2 correct ones, and gone along and picked up the rest of it correctly. Of course, it could have happened that I didn't quite align. I drop a character and I end up in the middle of something else. And so I write out another piece of garbage. But since the codes tend to be of different lengths, I'm wiggling along, writing total nonsense. which maybe I'm very good at. But in the end, what's likely to happen is I'll by chance realign. And by chance, what I think is a character will come at the end of what was one of those characters. It'll just wiggle along by chance. And once it realigns, everything that occurs after it is correct. Is this useful? Kind of shaky. If you had a lot of things which it could go a long time without realigning, that's a curiosity. Just sort of showing you one that you make the error and you get total nonsense, maybe for a while, maybe for only one character. So that one's okay. So let's take a look at the final one. Anybody got an answer for the third one? Sorry, that was just a think. Any answers for the third one? This was a real thinko, sort of off-the-wall question, that you've got a message sitting here, and it could be at the end, but it could be at interspersed. In fact, for figuring it out, it's logically, the math is easier if you think of these extra characters as being interspersed here. The math just works out that way. But you have to have enough extra bits such that if one were flipped anywhere in here, including here, you could figure out where it was. By examining, by doing the decoding, and by looking at these particular bits and doing some arithmetic. But these particular bits have a number of possible values. And if I had 1,000 bits that I wanted, I want to add on a number of possibilities here such that those possibilities, the number of different possibilities, different bit strings, different patterns I could have. I don't mean just like 10 or 15 or something like characters. I mean all possible characters, all possible bit strings of 15 bits. So that's 2 to the power 15. That's 32,000. So I want to have something in here that has enough possibilities to be more than 1,000 by this amount. Well, I'll jump to an answer and I'll say, if I happen to put 10, curious, I'm talking about bits, and curiously I'm writing decimal numbers that look like they're binary, but they're decimal, okay? That's our current interpretation. These 10 extra bits have this many possibilities. Each one is a 0 or a 1, and you multiply 2 possibilities times 2 possibilities times 2 possibilities 10 times, and you get 1,024. Some of you know that off the top of your head. Others will just sit there and say, I wonder if he's making it up. I wonder if it's true. Just like you do in your normal classes. And so if we have 1,024 possibilities here, it is possible, 1,024 possibilities. I only have to cover 1,010 locations where the mistake could be. So this wasn't really a question on, this was sort of a big cheat as a question. It was coming back to the comments about correcting errors. And in fact, this is precisely, the math works out that this can be done. You tack on an extra to 1,000, you tack on an extra 10 bits. The 10 bits have 1,024 possible things, patterns that they could represent. Gee, each pattern could tell you a location. You only have to say 1,010 locations. 1,024 is plenty. So you can get away with it, that. All right. That was a cheat as a question, but hopefully some people had some fun with it. Okay. Thank you very much. And I think we're ready for a little break.